Okay, so uh, okay. Okay, so uh, okay, so this is my submission for our single displacement reaction lab. So I did these pre-lab questions, but they weren't required, so I won't go over them. So my procedure. So my procedure was very meticulous. The first few steps are just, I assigned each solute to a row so to not forget which row they're in, then fill up each solute halfway up, use each solute to halfway fill up 3 wells in their given row because there are 3 metals, and then I assigned each metal to a column and put the containers behind those columns to not forget the order. So, very meticulous. And then after that, for the bulk of the experiment, step is to go through metal by metal so as to make sure that I've dropped one piece of metal in each solute while taking meticulous notes of the results. And then this is just an additional step to make sure if one is unclear about the details of a reaction which might have occurred, one could simply redo the reaction within a test tube to get a clearer view of it. And finally, one has to dispose of all chemical waste in a container with a tight-fitting lid labeled as hazardous waste. Okay, so moving on to the observations. So there are a few interesting observations to go over here. First of all, neither zinc, copper, nor magnesium reacted with water. I think this is actually a time frame thing. I think magnesium actually does react with water, or at least yeah, I think if you give it some more time, and I know magnesium does react with warmer water, but given our experiment and given our time frame, none of these metals reacted with water, and you can see very clearly that copper is the least reactive of these metals because it did not react with any substances, any of the solutes. You can see that zinc is the second most reactive because it reacted with about half of the solutes. And you see magnesium is the most reactive since it reacted with most of the solutes. Okay. Now I guess let's just go through. Right. So for tin sulfate, zinc. This was very interesting. It crystallized and became like darker gray. And afterwards, I prodded it with the toothpick. It was kind of like a cracker, which that's the consistency is very brittle, which I thought was interesting. For magnesium, it started bubbling, which, as you can see, means that a gas was created and a black precipitate formed. And an interesting thing about this is you can see the other time that magnesium reacts with sulfate solute. Here with copper sulfate, the exact same thing happened. There was gas created and a black precipitate was formed, so that's pretty interesting. When magnesium reacted with zinc nitrate, it turned black and created bubbles, so gas was created, or gas was formed. Then when zinc reacted with hydrochloric acid, there was some light bubbling, but you can see when magnesium reacted with hydrochloric acid, not only did bubbling occur and gas was formed, but also it started dissolving. And then right, so here's the copper sulfate I was talking about before. So for zinc, it just turned black, which was very interesting. I think, yeah, these two results, I think they're fairly similar in some ways, which is a little bit interesting, but definitely not as similar as these two results. Yeah, and then obviously, as I mentioned before, the same thing happened for the tin sulfate and copper sulfate when magnesium reacted with them. And then finally, magnesium reacted with iron 3 chloride. So there was light bubbling and it turned bronze, and you can see with the iron 3 chloride and with zinc nitrate how magnesium is more reactive than zinc since it reacted and zinc did not. Okay, so analyze and interpret numbers 1 and 2. So these are the correct equations. I don't think there's all that much to go over. Maybe I should go over just how these equations are, I guess, formed. So first one, you can pretty easily look up the reactivity of polyatomic molecules, but another I think better way to do it is you just find the charge of the, let's say for this example, tin, which is bonded with it, and then you use that to deduct the charge of the polyatomic molecule by this number. See how many it takes to fit with tin, and then you use that number to then you switch these two elements, and then you use the number the polyatomic molecule's charge number to figure out the combination which is necessary between these two molecules. In this case, it was 1 zinc and 1 sulfate. Yeah, and that was pretty much for all of these. That's how it worked. Okay, right, so now on to question 2. Sorry, I didn't even scroll down for this. But that was just, the question there was just for each single displacement reaction that occurred, write the corresponding balanced chemical equation, which is what I did. So, question 2, lithium metal reacts with water. Is lithium more or less reactive than magnesium? And I wrote lithium is more reactive than magnesium because it reacts with water, whereas magnesium does not. Additionally, lithium is, so I didn't realize that we were going to be talking about, I said reactivity series, should be activity series, yeah. So I didn't realize we were going to be talking about the activity series later. I just remembered this from grade 10 science, so I looked it up, and lithium is very much higher up on the activity series than magnesium. So that is, yep, why lithium is more reactive than magnesium. Right, so the next question is, write a balanced chemical equation to represent the reaction of lithium with water. Right, so both lithium and hydrogen have a 1 plus charge, so, and oxygen has a 2 minus charge, so for its H, so you simply just switch Li and H, and since oxygen has a 2 minus charge, there should be 2 Li's. Since Li has a 1 plus charge, it's just the same with hydrogen. So this was a very simple equation. Okay, conclude and communicate numbers 3 to 5. So rank the metals you have tested in order of reactivity, beginning with the most reactive metal, also including lithium. So lithium is the most, then magnesium, then zinc, then copper. And you can see that based on the fact that magnesium reacts with most of the solutes, zinc reacts with about half the solutes, and copper does not react with any of the solutes. And we know for a fact that lithium is more reactive than magnesium, as we have shown above. If an element which is low on the reactivity, I didn't read the question. Explain how an activity series of metals can be used to predict single displacement reactions. Okay, if an element which is low on the activity series reacts with a molecule, each element which is above that element on the activity, I keep messing this up, sorry, on the activity series must also react with that molecule. So basically what this means is, let's say you're doing an experiment and copper reacts with some solute. Okay, so now you know that all of these other metals, zinc, magnesium, and lithium, should also react with that solute. So you can use that to make predictions about, you can use that to make predictions for later in the experiment. Yep. Okay, given that lithium reacts with water and that magnesium does not, do you expect lithium to react with hydrochloric acid? If so, write a balanced chemical equation to represent this reaction. Okay, since magnesium reacts with hydrochloric acid, lithium must also react with hydrochloric acid, since lithium is more reactive than magnesium, as is shown since lithium reacts with water, and magnesium does not react with water. So because we know lithium is more reactive than magnesium, because of how lithium reacts with water and magnesium does not in our time frame, and given the temperature of the water and all that, we know that lithium must also react with hydrochloric acid, and the equation would just be simply Li plus HCl equals LiCl plus H, because Cl has a 1- charge and both hydrogen and lithium have a 1+ charge. So me a little bit later, I didn't realize before, but I actually had gotten these two formulas wrong. It's actually, since hydrogen is as it says actually, here it reminds us that hydrogen is a diatomic element. So it's actually these reactions have result in H2, not just one hydrogen. So yeah, that's all I wanted to say. And also, I'm fairly sure this video does not have a time limit. It did not say so in the description of the project, but if it does, I am sorry. I think I might have gone over it.